What affects resolution in XRM? Resolution in microscopy is defined as the ability to discern two separate objects. For example, electronic devices contain many components connected by traces with a large variety of size. Many of the components and traces can be distinguished, but a few of them are a bit too close. Digitally zooming in, we start to see that separation again, but eventually the limit of digital zoom is reached and the clarity starts to degrade. In XRM, a series of 2D pixel images are acquired at different rotation angles. Using this image sequence, a model of the original sample is reconstructed as a 3D array of volumetric pixels, known as voxels. The ideal resolution of the XRM system, referred to as voxel resolution, is determined by the pixel size of the detector and the magnification of the instrument. A detector with smaller pixels produces better voxel resolution. This comes at a price though, since the same signal is evenly distributed across the detector surface, reducing the signal-to-noise ratio in each voxel. In addition to having access to detectors with different pixel sizes, electronic pixel binning, the process of combining the electric charge from adjacent pixels, can be utilized to obtain the best balance between resolution and signal. The other element of voxel resolution is geometric magnification. Increased magnification resulting in higher resolution is obtained by moving the sample closer to the source and the detector further back. Voxel resolution is only part of the picture in XRM resolution, as it represents an ideal scenario. Real-world effects including instrument and mechanical stability and source focal point size must also be taken into account. The resolution with these effects is referred to as spatial resolution. Relative motion of the source, sample, and detector reduces the resolution of the system. This can come from environmental issues like vibration, or systematic issues like bearings in the sample rotation stage. In order to minimize the effects of vibration, the components in high-resolution systems are attached to a heavy, monolithic base that floats on air. Additionally, the sample rotates on an air isolation bearing. Source focus size is ultimately the resolution limiting factor in most systems. For a typical experiment, this is on the order of several microns. To obtain sub-micron resolution, a specialized source with small spot size is required. It is also important to remember that imaging is more than just resolution. Balancing resolution with field of view is also important in bringing sufficient context to the analysis. The best approach to XRM is holistic, taking into account the voxel resolution, spatial resolution, and field of view. Having access to a multitude of tunable parameters including filament type, focal spot size, sample and detector distances, and detector pixel size are all important in achieving the best results.